This is the table of contents showing what the topics are for this project and exactly where they're located on the video timeline. I made 3 videos, a series of 3 on this topic, and if you search YouTube for my name, Marty Plecki, you'll stumble across them. This particular video is on making metal film strip spot welder, which is what the battery application is all about. I bought 2 spot welders after trying to cobble together something on my own, and that cobbling worked out okay, but I did things like made bad spot welds, and sometimes I blew holes in the top of the batteries, so I had to replace them. So I bought 2 commercial spot welders, and I had pretty good success with this one. You've probably seen this on the market if you're into this kind of thing. But it was starting to not make such good spot welds, and I hooked up a voltage source at about 16 volts, and I blew the MOSFETs out of this guy. So I tried to fix this, but as much as I enjoy the electronics, I was not able to get this guy to work again. So I bought a second one. That's this one here, and I thought that I was going to have a really good luck with this because it has more MOSFETs in it than that red one. But as you can see, well, maybe I hope I get this right there. Is a trace that is blown out. It's blown out on this side and on the back side. So that was after about I don't know, maybe 10 spot welds. But if you look closely at this thing, here's the positive, and it goes right across this bus to this other contact. So you don't really have to use this. You can attach your both red leads, one to the battery and one to this the probe, right together. They don't have to go through this. So I was able to use this for a little bit longer, but I never got this guy to make good spot welds, even at the highest power. So again, I put in a higher voltage source, and I blew these MOSFETs out. One of the reasons why that battery was not giving me good spots is it may be getting toward the end of its life. I calculated the internal resistance on this thing. That's what this number is here. Internal resistance is 0.35. And I'm going to show you how to do that. So internal resistance of a battery can be calculated with this formula. Internal resistance equals the voltage with no load minus the voltage with a load divided by the voltage under load times the resistance, the load resistance. So I'm going to show you how to do that too. So here's the battery pack that I'm using now. And this is a couple of high wattage resistors. Both of them are 10 ohms, and they're linked together, so the total is about 20. But I measured those with this multimeter, and got exactly 21 ohms. So I'm going to take the no load voltage of this battery pack here, which I made. So the load voltage of this thing is 16.02. Now I'm going to hook up this resistor to both leads of the multimeter and test the under load voltage. 15.99 or 98. So we'll go back to the page here. So 16.02 minus 15.98 divided by 15.9 times 21 gives 0.05. So this battery has that kind of internal resistance, and that one has 7 times that internal resistance. So this battery is going to be able to make much better spots than the other one. If you get something from this video, pause it during the video and hit the like or thumbs up icon. If you think it's pretty interesting, hit the subscribe button too. The subscribe does not cost you anything. It doesn't obligate you to anything. It just allows you to be notified when I make another video. And you can unsubscribe anytime by hitting the unsubscribe button just as easily. If you wait till the end of the video, you'll either forget about hitting the like and subscribe button, or the video will end before you get a chance to do that. I watched a whole lot of videos looking for the things that I needed, or the knowledge that I needed to make a spot welder on my own. The links to some of those, the more important ones for me, are below. Some of those used a bank of capacitors as the source for the energy to make the spot weld. There's 2 problems with this approach to spot welding. The first one is if you don't have enough capacitors, you may make poor welds. So you'd have to solder more capacitors in place to have more energy to make a good weld. Or if you're using thinner material, or switch to thinner material, and you have a set amount of capacitors, you might blow a hole in a metal strip or blow a hole in the battery because you have too many. So that means you'd have to take capacitors out. That's not very convenient. Also, when you're making a spot weld with that kind of setup, in the case of the capacitors, there's no switch. And when you put one probe on the metal you want to spot weld, as soon as you put the other probe down, the capacitors discharge. So the metal underneath this probe is in contact with the metal on the bottom. But this one here, as soon as you touch it, it discharges. But as you can see, there's a flexing of that metal going on before it touches the metal underneath. And this one won't have any contact between this one and the one underneath, and there won't be a spot weld here. So for me, I didn't want to bother with that capacitor bank as a solution for my spot welding. Another type I saw uses a switch to connect a battery to probes and make a spot weld. But it depended on how long you held the switch, and the ability for a human being to make repeatable hold times is really not all that great. So you might make it so fast that hold the switch and release it so fast that you don't make a good weld, or you might hold it so long that you blow a hole in the top of the battery. So that's why I decided to use a timer that's independent of how long the operator holds the trigger switch. The 555 timer is pretty inexpensive because it's been around for so long, and it's also pretty reliable, again, because it's been around so long. So I'm going to show you the circuit diagram I decided upon. This is the circuit diagram for the entire project. This left side of it, this is the 555 timer right here. The left side of this circuit here runs the or produces the pulse that triggers the weld. This circuit came from DYI Tech, and I've got a link of that below. When this switch over here is pushed, the trigger, which is number 2, this trigger takes it to ground. The timer starts. Now this 500 ohm resistor, I replaced that with a variable resistor that can go from 0 ohms to I don't know, maybe 100,000, but I use it somewhere in the 400 to 1,000 ohm range to get dwell times or weld times of 0.03 to 0.07 seconds, which is about 30 to 70 milliseconds. In this timer, the trigger is pin 2 and the output is pin 3. Now, in DYI Tech's video, this thing runs an LED. But I watched a whole bunch of other videos. Among them is how to run a MOSFET. So I knew that this pulse would drive a MOSFET. So that's what this is. This is a MOSFET right here. When this push button is pressed, a pulse of the same voltage, the battery voltage right here, comes out and turns this MOSFET on, which sends about 2 amps through this solenoid, and this is a solenoid from a car, which makes contact here and sends a pulse of electricity to these 2 probes. Now, this is the positive side probe, and this is the negative side probe, and the weld happens. Now, the reason I chose to do this solenoid instead of a bank of MOSFETs is because I watched another video on how to repair that red commercial spot welder. And this video was from a guy named Luca. Very, very knowledgeable fella. Has great videos on. He explains electronics really well. He's a very smart person. Anyhow, one of the things that he said about MOSFETs is if you use them in this kind of application where you have to have a bank of them, somewhere between 5 and 10 MOSFETs to carry the load, they have to be matched. Otherwise, just like in this example, he's got 1, 2, 3, 4, 5, 6, 7, 8 MOSFETs, but if they're not matched, say these 2 MOSFETs are on the low end of the tolerance for the on time of the MOSFETs, and the rest of them are on the high end. These 2 guys will carry all the load until they blow out. And then once they're blown out, these don't work anymore because it's a short circuit, and as soon as you touch the probes, you blow a hole in the top of the battery. I wanted to be sure that everything worked before I spent a lot of time making it look nice. Buried in all this wiring here is a 555 timer. The circuitry around it will deliver a 0.018 second pulse of electricity to this solenoid, which will connect these probes to the battery over here and deliver a spot weld. Now, I'm not proud of the wiring, but I am pleased because it works. And I'll just click this this little button. It's a switch, and you can hear the solenoid fire. So let's see how it works for a spot weld. It's good. So I'm pretty pleased. And I can adjust the duration of the time up or down with this variable resistor. And there's a capacitor over here, so if I need to change it in a bigger way, I can do that. So I'm pretty pleased. Not proud, but pleased. Right now I'm checking the current draw for this circuit buried in the wires here. I've got it hooked up to the about 11 volts. I've got it set at 50 milliamps, and right now it's reading about 10 and a half milliamps. I'm going to trigger the circuit, and you see it goes, it jumps up to about 15 and a half. Now I have the meter connected to check the current draw for the part of the circuit that runs the solenoid through the MOSFET. I had checked it before without the quick pulse, just running the solenoid, and it's under 2 amps at 11 volts. But I'll trigger this circuit right now with the probe switch. And you can see that it barely goes up to 1 amp because it's such a quick pulse. And again, the meter is lagging, so my guess is it's the full 2 amps or so going through there. But anyhow, this MOSFET can handle up to, I think, about 30 amps or better. So this is well within the parameters for that MOSFET to function for a long, long time. Another really good video on how the 555 timer works, which was very interesting to me and helps me understand what would go wrong in the circuit, so that if something does go wrong, I can fix this one, unlike the other commercial spot welders that I'm having a difficult time trying to fix. That video is from Jim Pytel at Columbia Gorge Community College, and again, I have the link below. I show this circuit diagram for the folks that are able to use it, and just a couple of things about what I added to it. This is a solenoid, so when electricity flows through here, it creates a magnetic field that makes this contactor work. Well, when the electricity stops, that magnetic field has to collapse, and when it does collapse, it sends voltage spikes to some of the components, mainly the MOSFET, which might make it fail over time. I found out that if you put a diode across here, it channels the collapsing field back around so that it doesn't create a voltage spike in this part of the circuit. I also added this capacitor here for preventing sparks across here, because if you don't do that, after a while, this may eventually weld these contact points, because there's so much current going through so quickly that it sparks and creates a lot of heat, even though it's very short. This capacitor, when this contact opens up, absorbs a lot of that spark, so that it reduces the likelihood that these will weld, or another way to put it, I guess, is increases the longevity of this contact or pair of contacts. I also put an LED in this circuit before the MOSFET as an indicator that all this works in case I don't get welds. If I know that all this works because this LED turns on, then I know that my problem is over here. I made this circuit diagram on a software called KiCad, KiCad. It's an electronic software. I don't recommend doing this because it took me a full 8 hours of study to make this, find out how to work the software, etc. Now, it looks nice, and it's a good representation of this circuit. But unless you're really into electronics, you would be wasting time trying to learn this. Anyway, one of the things that puzzles me about why the software does this is right here. This representation of the 555 timer doesn't have the pins in the right spot. Pin 1 here, pin 2 here, pin 3 over here, pin 4 over here, and so forth. And that's not how it is. So I'm going to show you what I ended up doing to complete this PCB for this project. So here it is. And this is the pin configuration of the 555 timer in real life when you're soldering it into a PCB. So pin 1, and there's a little circle right there, or dot there. So here's pin 1, 2, 3, 4, 5, 6, 7, 8. And you have to make your components match up to these pins in order for your circuit to work. So this was the first iteration of a circuit that I could actually use to make a spot welder. This is probably the second, third, fourth, and fifth iteration. And you can see that I turned the chip around and started to locate all the various components on a PCB. And this is probably around the 10th after a lot of erasures. So here's the left side of that circuit that creates the pulse. Here's pin 3, the output, and it's going to this MOSFET. And then I connect this side to the solenoid and this other side to the solenoid to trigger it and send electricity to the probes. So that's the layout that I wanted to produce. Here's the battery. Here's that switch, push button switch that gets connected here. All right. And this is the real life result. I translated this diagram onto this PCB that I had for probably 25 years or more. I outlined or made the traces by putting nail polish on the places where I want the copper to stay. I have an etchant here. This is another 25 to 30-year-old thing from Radio Shack. Anyway, I'm going to put this little circuit board in that etchant, and what will stay is what's underneath the nail polish, and what'll go is what the copper that you see. This is ferric chloride that will etch the copper off of this PCB. The PCB is etching in the ferric chloride right now. It should take about 15 minutes. The copper is coming off, and it turns this amber or dark orange colored liquid a little black. You're supposed to agitate it, and it should be completed in about 10 or 15 minutes. All the copper has been etched off of here now, and I'll remove the nail polish with a nail polish remover and then get to soldering the components on. So here's the circuit board with the nail polish cleaned off with a nail polish remover. I'll have to make sure that there's no continuity between the traces where I was a little bit clumsy with the application of the nail polish. This is certainly not professional, but it should work just fine. This is the solenoid. It's from a Ford truck, I think. I bought that at Amazon. Where I got all these components, I put below. So here's the 555 timer, and here's the various components. This is the variable resistor. These leads go to the push button. The push button is located on this probe. This is the push button. It's got a really small button on it, so it can be a pain to push it. So I put this little paddle in here. This is the 555 timer. I bought 10 of these for about $7 from eBay. Anyway, I went through 2 of these while I was building this circuit, destroyed 2 of them. So I found this module that I can plug these into and take them out easily. It's another way to be able to diagnose anything that might go wrong with the circuit, although it seems to be pretty robust at this point in time. This is a MOSFET, and I got this MOSFET from a BMS that came with a battery pack that I bought from Battery Hookup. And that the battery pack was attached to this BMS. This MOSFET and this one are the same as the one that's in my circuit. So to get them off, what I do is I put a heat gun on this thing, and when it gets up to about 300 degrees, you can just pick these guys right off of there. So MOSFETs, transistor, anything else that you can identify from here. And here's some more examples. This is a couple of MOSFETs that I got from I don't remember where, but it's IRF 730 N-channel MOSFET that can handle 55 amps and 700 volts. Here's another one of the one that's in my circuit, and another smaller MOSFET that probably, well, obviously can't handle as much amps and voltage as the ones above, but might be useful in another circuit. Let's do some welds. So here's what I would call a pretty dang good weld. Now this battery is right at 12 volts. It could be at 12 and a half, and I'd get a better result maybe. Anyway, in this particular weld, this material here is about 10 thousandths of an inch thick, and this piece is 7 thousandths of an inch thick. I'm going to show you what happens when the material is thinner. So these guys, both of these are about 5 thousandths of an inch thick. Well, as you can see, the power was enough for this thin material to just vaporize it. When it's 5 thousandths thick material, I can take this variable resistor and dial it back to about 300 or 400 ohms, and it will reduce the on time of this timer and weld the 5 thousandths thick material, or I can increase the resistance in here, make the dwell time longer, and weld thicker material like this. That's about it for my project. If you liked it, of course, like and subscribe if you got something from it. And have a great day. I was waiting to finish this project in order to finish this battery pack. This is a 25 amp hour, 12 volt or 12 to 16 volt battery pack for some application that I'm going to use in the future. But let's make a few more spots. Yep, I got 2 more to go. That's it for my project and this video. Again, if you got something from it, like and subscribe. Have a great day.